Good afternoon, friends. Today we will discuss on study on low dropout voltage regulators. In this topic, I will first introduce the LDOs, then what is the need of LDO in typical power management system, thereafter working principle of the proposed topology or LDO, proposed LDO, then LDO regulator characterization. Thereafter, here we will characterize LDO, how what are the specified terms are really required to characterize an LDO. LDO regulator efficiency, this is also an important factor. Next, I will classify different types of linear regulators. LDO comes under the category of linear regulator. Stability issues of LDO. Here I will show different compensation techniques, frequency compensation techniques, which are usually available in literatures. Transient response attributes of LDO. Next, power supply rejection PSR by LDO. It is one of the most important advantage through LDO. That is why we will go for its discussion. Next, design method of LDO. How to design an LDO. And lastly, current research on LDO. What are the researchers are doing throughout this world on LDO. Finally, summary and assignment. The study of power management techniques has increased dramatically to the vast increase of portable, handheld, battery operated devices. The power management techniques required to make the system portable. Secondly, handheld and battery operated devices. Now, the improvements required to improve the device power efficiency as well as the operating time for the device, to increase the longevity of the device. Now, in this context, LDO regulators are essential part. It provides a constant voltage supply rail. Suppose input voltage is VDD is 3.3 volt, we are stepping down the voltage through LDO and we want to achieve, say, suppose 3.1 volt. The output supply voltage should be fixed one, that is a stable one, and that can be provided through these low dropout regulators. Next, suitable for on-chip power management system. Presently, the research going on to make the load capacitors and all the necessary components within the chip, that is integrated within the chip, everything will be within the chip. So, on-chip power management can be possible through on-chip LDOs. Now, a power management system usually contains several LDO regulators and switching regulators. We will show that the LDO regulators are suffering from poor power efficiency. Now, to manage this problem, we generally use switching regulator at the front end. That means the power input will be stepped down to a large extent by the switching converter to achieve the higher efficiency, power efficiency. Thereafter, I have already introduced that it has small LDO can provide the lower output ripple at the output voltage. So, LDOs are provided. That means LDO can be used as a post regulation. Here you can see that supply voltage is here, raw supply voltage. We want to regulate it and step down this supply voltage. For this, this supply voltage is through switching regulator, it is stepped down to a large extent, large input variation. Thereafter, some amount of voltage, say 3.1 volt to 2.9 volt, 200 millivolt dropout is done through these LDOs. So, high power efficiency as well as low output ripple can be achieved through this composite module. Now, the working principle of conventional LDO. It consists of an error amplifier, this is an error amplifier, and pass device. The output voltage is sensed through these feedback registers, and this is compared with the reference voltage Vref. Sorry, the reference voltage is then, the error voltage is then amplified, and the set the base voltage of the pass device, and pass device is the mother of all current source. It can provide the huge current for the load device. In CMOS technology, we use PMOS pass devices as LDO. What are the reasons behind it? I will briefly explain later. Now, depending on the orientation of the pass devices, the different types of LDO can be made. Now, LDO regulators characterization. In this context, I will briefly explain about LDO regulator specification, that means steady state specification. Steady state means when output reached at its steady state value. At that time, what is the fluctuation, what is the significant deviation occurs at the output voltage due to the change of input supply voltage or the load current. Dynamic state specification, it is occurs at the transient moment. That means when a current step has given from 0 to its maximum value, at that time what is the change occurs during this transient period, that will come into the category of dynamic state specification. Next, high frequency specification. High frequency means we will discuss about the power supply rejection ratio and all other things in this category. Now, first one is the steady state specification. First one is the line regulation. First, we have to define the term line regulation. It is defined by the ratio del V out by del V in. That means with the small change of input voltage, that is supply voltage, how much change occurs at the output after its arrival in steady state, that will defined by this ratio. And if you model it through feedback concept, it is the feedback register beta, it is the error amplifier A beta is the loop gain. You can see that line regulation del V out line is a function of, it's a simple analysis, you can do it by yourself, is a function of A beta, loop gain, GM, transconductance of the pass device. I already introduced what is the pass device, and ROP. ROP is the output resistance of the pass device. So, if we can increase the value of A beta loop gain, then we can achieve better line regulation. Next, load regulation. Load regulation means there is if there is some differential change of load current, how much change occurs at the output when it reach to the steady state value. And same same diagram we can use for the analysis, and you can see that V out load is a function of ROP by 1 plus A beta. That means it is also depending on the factor A beta loop gain. Now, temperature coefficient. We have seen that in the two terminal of LDO, one terminal is connected with the reference voltage Vref. So, I think you all have studied about band gap reference. So, reference voltage is provided through band gap reference, and their utmost care should be taken to make it temperature independent and supply independent. But sometimes what happened, that due to the small change of temperature, the reference voltage may vary, and due to this temperature variation, the output voltage will also be affected, and this is given by this expression Tc equal to this. Next, dynamic state specification. First, I will introduce about load transient. Load transient means when load current, we used to model the output load as a load current load or resistive load. Suppose a load current is varying from 0 to its maximum value. At that time, during this transition period, what will happen? Now, the output voltage will start a quasi static condition, will go into nonlinear fashion, that is called slewing phase. This is called slewing phase. Thereafter, the settling phase will come. That means when the transient load transients occurs, at that time two different phases will take place. One is slewing phase, another is settling phase. Here it is not, we are not discussing about how to determine the settling time or slewing period, because that will come under the category of control system, but I just introduce these two phases. Now suppose there is some change occurs at the load current, the load transient parameter will determine the capability of the LDO to regulate the output voltage with the change of load current or line voltage. Line voltage means the supply voltage. So the regulator should respond quickly with the change of the load currents, and this is given by del V out. The output change is a function of I max, maximum load current step, which I have shown 0 to I max, multiplied by delta T. Delta T is the total response time by output capacitance C out. Now this C out, if the C out is high, that means output capacitance, load capacitor of the regulator is quite high. At that time the output voltage, load transient parameter, load transient, the output voltage change due to load transient will be less, and delta T is approximately inversely proportional to the loop gain. So for high loop gain, the load the variation of the output voltage will be less. Now the response time means the charging and discharging of the load parasitic capacitance, that is slew rate. If the slew rate is less than the loop gain bandwidth, then what will happen? There will be a spike occurs at the transition period. That means when it is going from low to high current step, at that time a spike will occur during this period. And this thing you can see if you go for on chip power management, that means on chip LDOs. Line transients also come into the same category. Line transient means the capability of regulation by the LDO due to the change, due to the variation of the line voltage, that means supply voltage. And here I will define one term, that is the amount of regulation, line regulation in dB can be given as 20 log base 10, 20 log base 10 output voltage ripple by input ripple, input voltage ripple. Next, power supply rejection ratio. Power supply rejection ratio is the one factor, important factor. If you go if you see the specification of an LDO, you will see that the power supply rejection ratio is this much, PSRR is this much at this particular frequency. That means it is defined as the capability of rejection of the power supply noise at a particular frequency. So, power supply rejection ratio is also an important and we can achieve better power supply rejection through LDOs. And regulator output noise, here the present research is going on and it has come due to the transconductance, the noise due to transconductance stage of the input devices in error amplifier. Next one is the regulator efficiency. Regulator efficiency corresponds to the three following terms. One is the output voltage multiplied by the load current, how much current is drawn by the load register or load current sink. B in is the input voltage, that is the supply voltage, I load plus I quiescent. When to bias the entire circuit, suppose error amplifier and all these, I think you must have done in cadence simulation, to bias some current is required, some bias current 60 microampere or 30 microampere in CMOS 9. So, that is called quiescent current. Now, two situation comes, one is the heavy load condition, heavy load, and second one is the light load. At the time of light load, I load is far less than I quiescent. So, at that time quiescent current is the determining factor, deciding factor to determine the efficiency. On the other hand, so if we can reduce the amount of Q current IQ, then obviously your efficiency will be more at light load condition and longevity of the battery operated device will be more. But the problem is that if you reduce IQ, that means your slew rate will be affected. And on the in the case of heavy load condition, when I load is far greater than IQ, at that time eta is solely dependent on the ratio of V out by V in. And if you see the most of the literatures, they are supplying the data of efficiency, their regulators efficiency at heavy load condition. So, if the input voltage is 3.3 volt and output voltage is 1.65 regulated output voltage, then obviously the efficiency in percentage will be 50%. So, you can see that if the dropout voltage is more, dropout voltage means the difference in voltage between VDD, that is supply voltage, and the output voltage. If the dropout voltage is more, your efficiency will be poor and poorer. That is why linear regulators are suffering from poor power efficiency. And we will go for LDO type of regulator. I will come into that point. Next, different types of linear regulator. Conventional linear regulator, which I have already explained, that by using BJT or PMOS type, I have already explained. Linear regulator with source follower. I have already mentioned that depending on the type orientation of the pass device, the different types of LDO can be made. The first one is the linear regulator with source follower. Then the improved version of the linear regulator with source follower, that is the replica bias source follower. And third one is the linear regulator with common source driver. Okay. So, this is the typical block diagram of linear regulator with source follower. Here the pass device is NMOS type and it is connected in source follower configuration. As it is in source follower configuration, that means the output resistance is very low. So, the load regulation through this configuration will be better. If you do analysis, you can see that. On the other hand, but it cannot be, it is not suitable in low voltage application. Suppose the input voltage, that is supply voltage, is 1.2 volt. You just take this case, and 0.9 volt is the output voltage, regulated output voltage, and threshold voltage suppose 300 to 400 volt millivolt. That means Vg is not getting sufficient headroom to accommodate the fluctuation of V in, because 1.2 to 0.9 and Vth is 300 to 400. So V in is now, Vg is not getting sufficient headroom. So it has the disadvantage that it cannot be used in low voltage application. So here I have comment out that fast load regulation and very good high frequency power supply rejection. I will show you the analysis procedure, how to do analysis to calculate the power supply rejection and load regulation, all these terms. And it has the disadvantage of this topology is not suitable for low voltage application. Now this problem is solved through the use of charge pump. Here artificially we are increasing the voltage Vg at the cost of charge pump, at the cost of using charge pump, and the accommodation of the voltage headroom problem is getting solved. And another advantage is that here due to this load current variation, the output the feedback loop is not experiencing the load current variation, because it is under different loop. The load current variation is not sensed by the feedback loop, this feedback loop. So it provides additional regulation headroom, that I have already told, improved load regulation, but the load regulation is limited by the amplifier feedback loop. Third one is the linear regulator with common source driver. Here I have already shown you the linear regulator with PMOS pass devices. This is also the same type of linear regulator. It has the advantage that it can be used for low dropout condition, achieves low dropout voltage without the need of gate overdrive, which we used to take at NMOS type pass device. Secondly, smaller silicon area required for the output stage, but it has the disadvantage of slow load regulation and poor power supply to noise rejection ratio. Now stability of LDO. If you analyze for this time, I am taking off-chip LDO with off-chip capacitor. That means load capacitor is of nanofarad or microfarad range, and these capacitors are not ideal one. So there are some amount of resistive component is existing in series of the capacitor. This will come if you model the load capacitor, this will come in series with the output capacitor. This capacitor is called RESR. You will see if you go for designing LDO with off-chip load capacitor, there the specification, in the specification sheet you must see that the RESR is this much of that capacitor. That is called electrostatic resistance, and this will Cout and RESR jointly will give a 0. From this structure it is clear that there are two poles. One pole lies at the output of the error amplifier, and the second one as the output of the output voltage at the output node, and this one will Cout and RESR will jointly make a 0. So these three will play an important role for the stability of the LDOs. Now these are the pole locations for uncompensated LDO. this is the pole P1, where C1 is the capacitance, which is equal to C1 is the capacitance equal to C error amplifier, C error, which is very less, you can neglect it, plus CGS of the pass device plus CGD. CGD is here. So, AV into CGD, it is Miller affected. So, AV into CGD. So, the first pole P1 omega P1 will be at 1 by R1. R1 is the output resistance of the error amplifier, R1 into C1, and AV equal to GMP multiplied by ROP, the transconductance of the pass device, and ROP is the resistance, output resistance. Now, if you calculate, if you want to know the location of the pole P2, then P2 will come, omega P2 will be 1 by CL. Here we are not considering the term ESR, because it is on chip capacitor. That means the capacitor will be within the chip. So, the ESR factor will not come. Okay. So, the advantage we also not being, we cannot achieve that advantage also, that extra 0 is provided by this component, that is also one of the drawbacks of this on chip LDOs. So, 1 by CL multiplied by RF1 plus RF2 is the resistance of the feedback resistance parallel ROP parallel RL. These are the two pole locations. Now, it is customary to compensate the high impedance node. For the compensation, it is customary to compensate the high impedance node. Now, the for on chip regulator, CL is very small. For this, so the P1, the fast stage pole will become the dominant pole. You know the what is dominant pole? P1 will become the dominant pole, and P2 will come at the higher frequency. P1 may be at 100 kilohertz or 200 kilohertz, and P2 will be at higher frequency. So, this way compensation is done. Now, in this context, I want to mention about the modeling of load. The load may be either current load or the resistive load. Here I have shown you the variable resistor, it may be current sink. So, current sink from the theory of circuit theory, you can see, you have seen that the current source is is in parallel with a Norton equivalent resistance, and that will be if the Norton equivalent resistance is maximum, then current source will become more and more ideal, and resistive load will come as it is, that is RL. So, the total output resistance now for these two cases will be different. For current source load, the output resistance will be like that, ROP parallel RF1 plus RF2 parallel R Norton. On the other hand, the output resistance for current source load. On the other hand, current output resistance due to the resistive load will come ROP parallel RF1 plus RF2 parallel RL. From the analysis and by inserting the typical values, you can observe that the resistive load will for the resistive load, the output pole the P2 will be located at much more higher frequency than the pole by the current source load. But for initial analysis, resistive load is better, but in for when you are going to define a system, and inside of the system when LDO will come as a component, at that time it should be modeled as a current sink load. Now we have different compensation strategies were evolved. I am going to show you different types of compensation strategies. We know that that folded cascode or cascode amplifiers provide better high DC gain as well as better frequency response, but it cannot be used in low voltage application. Is it okay? Low voltage application, it is not suitable. For this purpose, I have concentrated the entire compensation strategies concentrated only on multi-stage amplifiers. That means that may be 2-stage or single stage, maximum 4 stages multi-stage amplifier is possible. Now it is the simple Miller compensation. AV1 is the first stage and AV2 is the second stage of the error amplifier. Cm is the Miller capacitance which we are intentionally giving, that is the external capacitance. And what Cm is actually doing, it is splitting the pole two poles, that is P1 and P2, which I have already mentioned, at 2 different frequencies. The omega 3 dB frequency will come towards the origin, that is at lower frequency, that means reduction of gain bandwidth, but the required phase margin, that is more than 45 degree, can be achieved through this Miller compensation. This is simple Miller compensation technique, SMC. Next one is the simple Miller compensation with nulling register. If you do the analysis, how will you do the analysis of the compensations for the compensation? You have to give a small perturbation here, V in, and you have to check the perturbation of V out. That means you have to compute the transfer function V out by V in, and from this you can get the location of the poles and zeros. Cm is actually responsible for pole splitting, but a high frequency, a zero, right-handed zero will come at high frequency, because if you go to the simple Miller compensation, you can see that at high frequency this will be short, and a feed forward current will flow through this path, and this path and this current both will be cancelled and zero will be produced. That is called right hand zero. It degrades the phase margin. To improve that, we are using a nulling register. What is its function? Its function is to nullify the zero. That means if Cm is here, the Miller capacitance, and if I can insert a resistor in series, then impedance of this path will be increased. So the feed forward current through this feed forward current at high frequency will be less. So the zero will not, the high frequency zero will not come. Now this zero, if you do the computation, small signal computation, what is the procedure of doing small signal computation? You know the small signal analysis. So entire thing you have to transform into small signal domain. That means GM into VGS, RDS, like that way, and from that you have to compute the transfer function V out by V in. From that transfer function you can achieve the different poles and zeros. You can see that through the use of this Rm, the 0 will come at Cm 1 by Cm Rm minus 1 by GML, 1 by GML. So, if Rm is exactly equal to GML, then we can nullify the resistance omega, nullify the omega z. Research means designers, what they used to do, it is very difficult to achieve the exact value of Rm, calculate the exact value of Rm. So, they used to do approximation, they used to enhance the value much higher than 1 by GML. So, what will happen, in place of right hand 0, a left hand 0 will be produced, and this left hand 0 will help to improve the phase margin. Rm will be far greater than 1 by GML in common practice. So, a left hand 0 will be produced. Now, this is SMC using multipath 0 cancellation. In this, we are not using the nulling register. Why? Because GML, the transconductance of the load stage, is frequency dependent. So, it is very difficult to accurately point out the value of Rm. So, what will happen? We are using a feed forward transconductance path that has the transconductance of Gm into F1, and here the feed forward current is coming at high frequency. So, if we can make I feed forward equal to Gm F1 into V in, then the 0 will be cancelled, the right hand 0. If due to this feed forward current, right hand 0 is produced. If I can cancel it through this transconductance stage, with the help of transconductance stage, then at the output we will not achieve any right hand 0. So, it is also one methodology, one compensation strategy, and people are using it. Now, we can go up to n stage of, theoretically we can go up to n stage of amplifier at the cost of reduction of bandwidth. So, nevertheless, the people reported up to 4 stages of amplifier. So, here we have shown the 3 stages amplifier, and for this compensation is called nested Miller compensation, because two Miller affected path there. So, Cm1 and Cm2, two Miller resistances are used, and this compensation is done at the cost of reduction of bandwidth.
So, here is dominant pole is due to which one?
What?
Dominant pole.
Dominant pole is the dominant pole, you have to do thorough analysis, otherwise you cannot say from outside, because which one will be the high impedance node, that will give the high dominant pole. Same procedure, NMC using nulling register. Nulling register is for to cancel the output right hand 0. This is the n staged amplifier compensation, MZC, multipath 0 compensation on NMC. These are the several techniques. So, through this compensation strategy, we can stabilize the LDO. Now, we will see the transient response attribute of LDO. First, for off-chip condition, here the diagram is for off-chip condition. That means off-chip load is there, CL. When a load transient occurs, I load is varying from low to high or high to low. At that time, if you can use the load capacitor to a higher value at the range of nanofarad or microfarad, that means off chip component, as an off chip component, it will store the potential energy equivalent to its output voltage. And when load transient occurs, due to this slow response time, the charge transfer occurs from this path to this. So there will be some deviation of output voltage like this way. If it is nominal voltage, then there will be some fluctuation of this output voltage, but for the off chip capacitor, LDO with off chip capacitor, this variation will be not much. That means settling time will be quite small. But in case of on-chip power management, when capacitor will come within the chip, at that time the capacitor value is of 100 picofarad maximum or less, 50 picofarad, then that capacitor is unable to supply the necessary charge at the time of load transient, that means when current step occurs. So that is also one of the challenge, how to settle the output voltage quite quickly without small variation, small change of output voltage. So here I have shown you the off chip capacitor, LDO with off chip capacitor. Now power supply rejection by LDO. For power supply rejection, we have modeled the LDO in its macro model form. What is macro model, you know? Macro model means you are defining the entire circuit through voltage control voltage source or current control voltage source and several passive components. So if you can remember the LDO structure, here I am not giving any feedback circuit, feedback register. The feedback register is not given here. So this is error amplifier. Here error amplifier is modeled by a voltage control voltage source. It is giving a gain of, say, suppose AV1, and this one is the pass device. It is modeled through voltage control current source, because here the gate voltage is controlling the entire current of the pass device, and RDS is the output resistance of the pass device. CT is the CGD, that is this capacitance is called CT, they are defining as CT, and CGS is called this way. RL and CO is as usual means load resistance and the output capacitance. This is the macro model form. Now a small perturbation is given at the supply line. Here it is the supply line, so a small perturbation is given, a small signal sinusoidal voltage Vs is given here. We want to see that how much output, how much power supply rejection occurs due to this LDO at the output. For this we are taking help of small signal modeling. AV1 into Vout is the fast stage, it corresponds to the fast stage small signal source. R1 is the output resistance of the fast stage. Cin is here, I have already said, get to source capacitance, so get to source capacitance. Gm into Vgs is generated pass device, RDS drain to source resistance, RL is the load resistance, CO is the output capacitance. Now a small perturbation is given here at the source node of the pass device, that is at the supply line. As noise is small signal phenomena, so power supply noise rejection can be modeled through small signal analysis. Now, if you do the calculation, you will be just astonished. Anyway, that V out by V is will be given by this expression. That means the small signal k. You are computing V out by V in terms of Vs. You will get this expression. It contains a 0 and 2 poles, a 0 and 2 poles. That is why I have excluded the analysis part, mathematical analysis part, because in every transfer function course will all the transfer functions will be like this type of cumbersome. So I have excluded this part. So if you do the analysis through mathematical analysis, if you insert the value, you can see that the power supply noise rejection occurs at a greater rate. That means it is in dB, V out by V is Vs in dB, and it is in frequency. So after 10 megahertz, the power supply noise rejection is occurring at a greater rate. So I already mentioned that in specification sheet or data sheet, there is one term PSRR is of such value at that at particular frequency. It is like that. Suppose 20 megahertz, the PSRR is minus 60 dB. That is quite high. So high PSRR can be achieved through this LDO. Now, design method of LDO. Here I am not concentrating on the design methodology of differential amplifier, because it is well known. Only thing is that how to design the pass device, M pass, because it is providing all the current, required current. The current may be of 15 milliampere to 50 milliampere 50 milliampere range. So this current is provided by this M pass. So it is a two-staged LDO with two-stage error amplifier. Here the two-staged error op amp is there. First stage is the error amplifier, second stage is for pass device. Here I have given artificially a compensation capacitor, but exactly what compensation scheme you will choose, that is up to you, because I have not gone for compensation part. I am only designing the pass device. The pass device so to keep it in saturation, VDS should be VDS should be exactly greater than equal to VGS minus VTH. So mod VD sat, it can be called as VD sat. So mod VD sat should be equal to 2I max, maximum load current, by mu P Cox W by L. It is quite known to you, this formula. From that you can see that W by L is equal to 2I max by mu P, sorry, it will be whole square, it will not come. W by L equal to 2I max mu P Cox VD sat to the power 2. Okay, this way, if L is known to you, suppose 400 nanometer, and from the technology file you can get the value of Cox or mu P. Cox will be actually equal to CGD plus CGS by 2. CGS and CGD can be achieved through that calculator part. Then mu p is mobility, it is given in the technology file, that you can easily get the approximate value of the width of the pass device, and generally it is huge in size at the range of 10 millimeter, like that. Now another strategy is LDO with single stage error amplifier. Here at the balanced condition, the current, bias current is flowing equally into two parts. Suppose 60 microampere bias current, so 30 through this part and 30 through this part. But when some load is given, at that time the pass device should be very high. So one of the load transistor can be used as a pass device. And what is the procedure of calculating the size of the pass device? Suppose 15 milliampere is the full load current, maximum load current, 15 milliampere, and your bias current is 30 microampere. That means in each side 15 microampere. So your equation will be like that: 15 into 10 to the minus 3 by 15 into 10 to the minus 6. Your bias current IB equal to, suppose, IB1 plus IB2 equal to 30 micro. So IB1 I have taken 15 divided by W of this device by W by L divided by W by L of that device. Through that ratio you can calculate the value of the size of the pass device. This is the general method, and other things you know, because how to bias the current, how to make all the transistors in saturation, how to make which one is the positive feedback terminal and which one is the negative inverted terminal and which one is the non-inverting, it is known to you. Now what are the research going on LDO? First one is the capacitorless LDO, on chip power management. That means here the load capacitor will be within the chip. Then what are the challenges? In transient response attribute you have seen that the load capacitor is supplying the required charge at the time of load transient. But if you go for on chip power management, that means load capacitor will be within the chip. So it will be lesser in value, that means 100 picofarad. So it is unable to supply the required current. So it is also one of the challenge, capacitorless LDO. Next, switching converters are cascaded with LDO. Where on this topic I am working now, that is called hybrid DC-DC converter. UC Berkeley, Professor Seth Sanders is also working. Here I have taken cascaded stage, after that the LDO stage, but there they are trying to make it parallel. That means cascaded stage and post regulator, that means LDO stage, will work in parallel fashion. Next, the people are trying for new compensation schemes of LDOs, and last one is the improvement of transient response to enhance the dynamic range. These are the 4 topics. On these 4 topics the people are working. In Texas Tech University, AMU, the capacitorless LDO, they are working a lot, Joe Silva Martinez and Sanchez Inancio. Now in summary, what we learned from this today's class, we have defined some different terms to characterize an LDO. Thereafter, working principle of LDO and classification of linear regulators. I mentioned the stability issues. There I have shown different compensation schemes which are usually available. I have shown their pros and cons. Next, transient response attributes, PSR by LDO, power supply rejection which is done by LDO, design method of LDO, how to design an LDO. So now it is the assignment, you can do it by yourself. I have not given stringent specification because at the first hand you should try by yourself, so enough liberty is given. So design a LDO which can step down the voltage from 1.8 volt to 1.5 volt with the load capacitor of 100 picofarad. The load current range is from 1.3 milliamps to 12.5 milliamps. The open loop gain of the error amplifier is 40 dB. Here you have to concentrate on both AC response, that is small signal phenomena, and that means transient response attributes, PSR, as well as stability. These three you have to consider at the time of design, these three things. You can so the open loop gain I have given is 40 dB. So if you are using 0.18 micron technology, then obviously a single stage amplifier, I think differential amplifier can do that particular job. Thank you.
Repeat the slide.